So in this video I want to go through an extended example that compares analog and digital communication. So what I'm going to assume is that I have an analog signal that I want to send from one place to another. I have two choices. I can use amplitude modulation, completely analog system, or I can run the analog signal, sample it with an A to D converter, converts it to bits, use digital communication schemes, and then put it through a D to A to get back the original analog signal. Which is better, particularly when you are trying to use the same channel for both. So I'm trying to make a very fair comparison here. So we're going to compare an analog and digital scheme going over the same channel. Our criterion for quality, our criterion for which one wins, is going to be the one that produces the largest signal to noise ratio in the final result. That's going to be our test to see which one is better. Now, as we've seen in previous videos, analog communication, because of the channel noise, is going to result in a noisy signal. And we already know what that signal to noise ratio is, and I'm just going to recall that result and use it. We're going to have to do a bit of calculation, though, for the digital channel. Now, I want to point out some things before we go into the details. Recall that because of the amplitude quantization in the A to D converter, that introduces an unrecoverable error. Once you quantize to bits, you cannot get back the original analog signal perfectly. So that results in a unrecoverable error that we won't be able to do anything about. But also, the channel introduces error because the probability of error in receiving a bit correctly is not zero. So that also introduces noise into the result, which makes the SNR go down. So guess what? No matter if it's analog or digital, the result is going to be noisy. And so we have to learn how to live with that, and that's just a fact of life. And more than that, which one results in the smallest amount of noise? Which one is better? And so here's the conditions for my little test here. I'm assuming I have a baseband signal that has a bandwidth of 4 kilohertz. I'm just using this as an example, a 4 kilohertz signal. And for the digital side, it's going to be sampled with a B-bit converter. I'm going to let the number of bits be a variable here to see what the effect of that is. I think you'll be a little bit surprised on how that affects the results. Well, so let's go through the analog system. I have to use a modulated scheme, and so we know that if you have a bandwidth of W, that the transmission bandwidth that you use in doing analog is twice that bandwidth. So we have an 8 kilohertz transmission bandwidth. And we also know from previous results that the signal to noise ratio of the received message signal has that formula. I do want to point out that I have not written the alpha from the channel in here, the channel attenuation. I'm just merging that with A. As you know, the correct expression has an alpha squared A squared, and so I'm just going to merge the two into one symbol, so we simplify the expressions a little bit. Okay, now for digital communication, we have to sample. And we're going to have to sample at a sampling frequency of 8 kilohertz, twice the highest frequency. Okay, and we also know that the transmission bandwidth is 3 times R for modulated BPSK, which is a very good signal set. So the data rate is going to be the sampling rate, 8 kilohertz, times the number of bits in that A to D converter, because we have to send the same signal every capital T seconds, T being the sampling interval. Use more bits, you're going to have to have a higher transmission bandwidth because the data rate goes up. So we're going to use this result a little bit later. So again, to repeat what I said on the first slide, the digital side of things, the final signal you get out of the communication system is the original signal plus the quantization error, which is due to the A to D converter's amplitude quantization, plus the communication error, the effect of PE not being 0. So we're going to figure out each of these and just add them up, and then compute a signal-to-noise ratio. So the quantization error we've gone through. So some more little details. I'm going to assume that the signal has an amplitude that's less than 1, so I can scale things appropriately. And if you express the final result out of the A to D converter and then a D to A in terms of bits, you get this for the formula. So to understand this, let's suppose we draw our diagram that we've been doing. So signal goes between -1 and 1, and we're dividing this up into quantization intervals somehow. So if you set all the bits in this expression to 0, well, what you get for a result is -1. So 0, 0, 0, 0, 0, however many bits we use, is going to correspond to an amplitude of -1. And when you set it equal to all ones, you'll get something very close to 1 if you evaluate this expression. So that's this formula does not really come out of the air. It's just trying to relate bits to an amplitude that's in this range. Okay. Well, when it's received, we're going to have we're going to have an error because the received bits aren't necessarily the same, and that's called a channel error. But because the fact back in the analog to digital converter, we did not get back exactly the amplitude we started with, we have already figured out in a previous video that that's the power in the error. 2 to the -2b, b being the number of bits in the converter, divided by 3. In this result we derived previously. But now we're going to look at the channel errors. Now the channel errors, the resulting error because of errors in the communication just revolve around the fact that the transmitted bit and the received bit are not the same. So we want the power in that error. And I'm going to write that in a kind of a new way. These angle brackets mean average. So that's a typical notation for mean average. So we're going to square the error in average to get an idea what the average power in the error is. If you go through the calculations, what you discover is just the average of the square of the difference between the two bits. So we have to figure out now what that average is, and it's a pretty easy calculation. So it's pretty clear when the bits agree that that difference is 0 and there's nothing that contributes to the average. The only term that we will get is when the bits disagree. So we could have sent a 0 and received a 1. We could have sent a 1 and received a 0. Well, these errors occur with a probability of PE, but the probability we send a 0 or send a 1 is a half. So that makes the total probability of that term being a half PE, total probability for this term being a half PE, and they all add up to just be PE. So it turns out this averaging term here is really quite easy to see. I do want to point out something else before we go on. Some bits matter more than others. Notice this exponent out here. This has to do with the fact that the higher bit, the one that has a bigger value of k here, if you make an error in that bit, it really affects the result for the error. If the smaller bit, where k is 0, doesn't have as much effect. So some errors and some bits matter more than others, and we want to see the overall effect of channel errors. Okay, so So I'm using my result that PE was the average value here as a constant, and to sum this term up, it turns out that's a finite geometric series, which we've already talked about, and once you do all those calculations, this is what you wind up with. Now, 2 to the 2b, I'm going to assume, is a whole lot bigger than 1, which is normally the case, and that's where the approximate sign comes in. And once you drop that 1 and simplify, you get 4/3 PE. So you get a rather simple result for the channel error. So that's the power in the channel error. We have the power in the quantization error. And so the final result for the SNR for our digital communication scheme is there's the signal power, of course, and I just add up the two powers from quantization and channel errors. Okay. So there's a little detail here, and that is we have to be fair about the transmitter power. I want to make the transmitter powers the same. So I'm going to recall something here. So recall for digital that the energy per bit, which is the critical part of the probability of error expression, is a squared t. Well, t is the bit interval duration, and so what's t? And t, as I wrote in the previous slide, is 1 over r. So r, the data rate, is the sampling frequency times the number of bits in the A to D converter. So relating it back to bandwidth and bits, this is the expression we get, and so you figure it all out. The amplitude squared, which is from the transmitter and the effect of the channel, is related to the energy per bit through this expression. So I'm going to take my analog expression and convert it into something that's related to what I call ES, which is the energy per bit times the number of bits. So ES is the energy per sample that's used in the communication scheme. I want to keep that the same between the analog and digital systems so I can compare them fairly. So our signal to noise ratio here is given by this. Notice the power in S disappeared because it's going to be the same in both expressions. I'm assuming basically it's 1 just to keep it simple. And here's PE. So it's for a QPSK thing, the result was 2 EB over N naught, and I've simply substituted in ES for that so I can explicitly take into account how many bits are being sent. So what I'm going to do, I'm going to plot this as the analog system as a function of ES over N naught. I'm going to plot the result of this communication scheme as a function of ES over N naught. And ES over N naught, remember, is the basically summarizes how much power and attenuation was used in the transmitter and the channel compared to the channel noise. So this is the axis we want to compare on. And I plotted the analog and digital cases here, the digital for 2 different number of bits in the A to D converter. As we showed, the analog is the simplest because the overall signal noise ratio for the at the output is the same as ES over N naught, so you get a straight line, and that's the equality line. So for 4 bits is the dash curve. For 8 bits, you get the solid red curve. It's kind of interesting. Let's see if we understand this. First of all, as the channel signal to noise ratio goes up, PE basically is going to 0. So what happens is you're left with the quantization error. So these are the limits of the quantization error. And as we know, the more bits you use, the smaller that error gets, which, since this is the signal to noise ratio, that means the SNR goes up. So that part I understand. If you go down to the other extreme, PE is basically a half, no matter how many bits you use, because the channel is really, really, really noisy. So that's why these two curves converge. In between, it's interesting that the 4-bit result gives you a higher SNR than the 8-bit result. And the reason for that is because PE for the 4-bit case is actually smaller than it is for the 8-bit case, because you're dividing up time less. You're only dividing it by 4 for every sample rather than 8. And that has an effect of producing a slightly bigger SNR in the result using 4 bits, but only for a while. Once the SNR gets big enough, the 8-bit becomes far superior. However, can't lose sight of the fact that the digital curves lie above the analog curves. So, in this comparison, the analog system is inferior, it's worse than the digital systems. This is despite the fact we introduce error in the A to D converters that we can never get around. It's clear that, at least in this comparison, that analog is not as good as digital. So digital wins. And that's the kind of analysis that you want to do as an engineer to figure out which scheme is going to work. You use some criterion like the signal-to-noise ratio for the final received message, and then you pick your design criterion, here is analog or digital, according to that choice. There's a little caveat here. I do want to point out that one thing that isn't fair about this comparison is that the channel bandwidth needed for analog is much smaller than that needed for the digital schemes we just talked about. The digital transmission bandwidth, like I said, is twice the highest frequency of the message, so it's just 8 kilohertz. However, for 4 bits you need 96 kilohertz, and for 8 bits you need twice that much. So, in some sense, this isn't a very fair comparison. So, what that means is that what happens if you make them the same? What happens if you constrain the transmission bandwidth to be the same for both cases? Well, it turns out that if you constrain digital schemes to work within an 8 kilohertz regime, you can show that amplitude modulation, the analog scheme, now wins. It always results in a higher SNR. It's kind of interesting. However, if you use more bandwidth than that, something like this, it turns out you basically cannot effectively use that extra bandwidth for analog communication. It doesn't have that flexibility involved. And then it turns out digital wins. So in the grand scheme of things, overall, this is one of the reasons why in modern uses, everything is being converted to bits and sent in a digital way. Now I'm going to talk about a situation in upcoming videos. We'll find out that you can actually send bits through a noisy channel with PE winding up being 0. And we're going to figure out how that works. It involves some very clever engineering, and we'll see that in the upcoming videos.